Okay, hi. I'm gonna make some adjustments here. So the video system I was using just was terrible. That's what you get. Anyways, this is test 3 review, and basically I'm working with test 3A from summer. It says summer 2019 on the top. Okay, and we want to kind of go through this just to make sure everybody's on the same page. And the first problem is to find any potential critical numbers. I see, kind of like find any potential critical numbers. So the deal for these is that to get the critical numbers, you have to find the derivative. So we're given a function y equals 2x cubed minus 6x. Okay. We want to find the derivative, set it equal to 0, and that sort of thing. So y prime is 6x squared minus 6. Right? And then the critical numbers will happen where y prime is equal to 0. Right? So in that case, we take 6x squared minus 6, set it equal to 0, and solve. Right? So we have 6x squared equals 6. In other words, x squared is 1. In other words, x is plus minus 1, right? Okay, so we've got 2 critical numbers there. The other places are where the derivative does not exist, right? Fortunately for us, or unfortunately, this expression right here represents the derivative. It is basically a way to evaluate the limit of the difference quotient, which we define to be the derivative. So for any value x, you're going to be able to get a limit out of that, and therefore it will be differentiable anywhere. So this guy, no, it's not going to give us any of these do not exist points, and we can conclude the only critical numbers are at plus and minus 1. Okay. Let's look at the next one. So here we have problem 2. Y equals 4x all over x squared plus 1. Okay. And it's the same game here. We want to find the derivative. So y prime, we're going to need the quotient rule, right? So low times the derivative of the high is 4 minus high times the derivative of the low is 2x all over the low squared. Okay. Then you clean up the numerator. So that's going to be 4x squared plus 4 minus 8x squared. That's all over x squared plus 1 squared. And you want to simplify that. 4x squared minus 8x squared is minus 4x squared, and then plus 4 all over x squared plus 1 squared. Okay, and then we need to play this game. I need to find where is it equal to 0. Okay, so you set this equal to 0. It'll come down to just letting the numerator equal 0, which is the way you do it for rational functions. Okay, okay, we can solve this. So x squared, negative 4x squared will equal negative 4. And then x squared will equal 1. And then x equals plus or minus 1. Okay, so 2 critical numbers there. Then we want to know where y prime does not exist. So you go back to the derivative here, and we're going to set the denominator equal to 0 this time. X squared plus 1 squared. Set that equal to 0. Square root on both sides, so x squared plus 1 is 0. And then x squared is negative 1. Uh-oh, we're in trouble, right? There's no x value such that in the real numbers where you square it, you'll get negative 1. Right? I squared is negative 1, but we're not working with those guys. Right? So the only 2 critical numbers will be at plus and minus 1. Okay, great. The next sort of exercises are the max-min on closed interval problems. So for these guys, and I'm using scrap paper, so I have to. Right, so for these guys, you'll be given a function t all over t plus 3, and then in an interval, and you have to find the maximums, the absolute maximum and absolute min on that interval. Okay, so this is problem 3. We have y equals t all over t plus 3. Okay. Okay. At first, and it's on the interval from, sorry, -1 to 6. Okay. So at first look, it seems that what's going on here? I need to still kind of do the same thing I did before. I need to find its derivative. So sadly, I have to do a quotient rule. So low times the derivative of the high, which is 1, minus high times the derivative of the low. And then we have, what, t plus the derivative of t plus 3 is just 1. Okay, great. And that's all over t plus 3 squared. Okay, clean it up. So I get t plus 3 minus t all over t plus 3 squared. Okay, so I have 3 all over t plus 3 squared. And that's my derivative. So now I have to find where is that thing equal to 0? And also, where is it undefined? So where is it equal to 0 first? Well, there's not going to be any solutions to this equation, right? If you multiply both sides by t plus 3 squared, you just get 3 equals 0, which is not going to happen. So there's no help here. There's no critical numbers that you're going to get from that equation. Then you want to know where the derivative is not defined. Okay? So this time I take the t plus 3 squared and set it equal to 0. And that's only going to happen when t is -3, right? Okay. So our only real critical number or potential critical number would be -3, but it's not even in our interval of concern. So we're not going to even work with that. Okay. Okay, so for Extrema on closed interval, what we do is take the endpoints and evaluate them in the original function, so this guy here, and also the critical numbers, but there were no critical numbers. So all we need to do is evaluate f of -1. So if I plug -1 in here, I get -1 over -1 plus 3, so -1 all over 2. And then if I plug 6 into here, what do I get? 6 all over 6 plus 3, which is 6 over 9, which is divide top and bottom by 3. I get 2 all over 3, right? Okay, so what does this tell me? Well, this guy here is the min, the absolute min on that interval, and then that guy right there is your absolute max. Oops, I ran off the page. That's going to happen. Okay. Okay, so all I was doing is taking my endpoints, in this case, and plugging it back into my original function. And then you look at the values that it outputs, see which one's the big and which one's the small, and then that's it. You can have more than one max, more than one min. Let's look at the next one, which is a trig guy. So this is problem 4. We have y equals 3 cosine x on the interval from 0 to 2 pi. Okay, so take its derivative. Y prime is 3 times negative sine x, right? Which equals -3 sine x. And then I want to find where it's equal to 0 on that interval. It's from 0 to 2 pi. So you think about the unit circle. I can divide both sides by -3. So I'm just looking for where sine of x is equal to 0, and that'll happen when x is equal to, well, what? Well, on the unit circle, sine is equal to 0 at 0, pi, and 2 pi. Okay. Y prime is defined everywhere. So the question whether or not y prime does not exist, well, no, it's never going to happen. So there's no critical numbers from there. These two, 0 and 2 pi, these 2 points here are actually endpoints. So we would be checking those anyways. Okay, so for the extrema on a closed interval, we need to check the endpoints. and then any critical numbers. Right? So the only critical number that wasn't an endpoint was pi. And then I plug these back into the original function and look for what's the max and what's the min. Okay, so if I plug 0 in for cosine, I get 3 times cosine. Cosine of 0 is 1, so I get 3. 2 pi, that's 3 as well. And then pi, cosine of pi is -1, so -3. And so we have 2 maxes this time. I have absolute maxes at the endpoints, and then there's an absolute min in between. Okay. Okay. The next set of questions are on the mean value theorem. And the mean value theorem graphically just says that if you have kind of an average rate of change, there'll exist some point where the instantaneous rate of change is equal to the average rate of change on the interval. So graphically, what does that look like if I'm going from A to B, and here's my f of A, and here's my f of B? Basically, there'll exist some point C in between f of A and f of B such that the tangent line at C, so maybe C is really closer here, the tangent line at C, its slope will be the same as the slope here. And written out, that means f prime of C will equal f of B minus f of A all over B minus A. Okay, one thing this immediately tells you, believe it or not, is that there's restrictions on what the sort of reverse derivative is. So, you know, we're used to taking derivatives like the derivative of x squared is 2x, but we can do this in reverse. Like the antiderivative is what we'll call it, of 2x is x squared, right? Okay, there comes a question, you know, is that the only antiderivative? And the mean value theorem will say, pretty much, okay, plus or minus some constant value, all right? So we'll see that later, and that's one reason why it's important. I know in my videos online, I kind of blow it off like, oh, we have to learn this. Well, I didn't mean to do that. Those are like my rehearsal videos. I don't mean them to be etched in stone, but at least, you know, it's important, okay, guys? Okay. So problem number 5, we want to determine whether the mean value theorem can be applied, and then if it can, find the C value such that this equation holds. So problem 5, they give you the function f of x equals x cubed plus 2x, right? All right, so first we have to make sure it obeys the criteria for using it. And first off, we need continuity on the closed interval that we're concerned with, and the question on the test says -1 to 1. So I asked that, is it continuous? And yes, it's a polynomial, so it's definitely continuous. And then secondly, is it differentiable on that interval? And it should be the open interval this time. Oh my gosh, oh, sorry about that. And yes, again, it is. You could look at the derivative. We'll need it anyways. So the derivative is 3x squared plus 2. And yeah, that thing, I can put any x value in there I want. So apparently that represents the limit of the difference quotient for the derivative, and you know, it works. Okay, so there it is. Okay, so I should be able to find some C value such that f prime of C. So when I put C into this expression, 3c squared plus 2, that should equal this slope. Okay, so this f prime of C is this right here. Now I need to figure this out. So f of 1. So when I plug, okay, so I'll just write it out. F of 1 minus f of -1 all over 1 minus -1. Okay, and the 1s and the -1s come from the interval. Okay, and now I'm going to plug those numbers into the original function. Right, so I get 3c squared plus 2 equals, when I plug 1, I get 1 cubed plus 2, which is 3. Minus, when I plug in -1, I'll get -1 minus 2, which is -3. And then all over 1 plus 1, which is 2. Okay, okay, so that's 3c squared plus 2 equals 6 over 2, which I hope is 3. And then subtract 2 over, so 3c squared equals 1, and then c squared equals 1 over 3. And then you could do the square root property, c is equal to plus or minus square root of 1 over 3. Okay, so this time we have two c values in the interval where it works. So both of these are in our interval. So that'll be your answer. There's two places where the instantaneous velocity is equal to the average velocity. You can think of physics-wise, right? Like, right, so let's do another one. This is number 6 on the test. We're doing the same kind of problem, a different function. F of x is e to the negative 3x on the interval from 0 to 2. Okay. So first off, I need to make sure it's continuous on the closed interval. And these guys are continuous everywhere, right? There's nothing I could put into the exponent that would screw it up, right? I put 0 in there, I put -1, fractions, it all works. So yes, this thing is continuous. Secondly, is it differentiable? And again, it has to be the open interval this time. I don't need the endpoints. Okay. So I find the derivative, f prime of x. With these kind of expressions, you just get back the same thing, e to the negative 3x, times the derivative of the exponent. It's the chain rule. So times -3. And this guy is clearly continuous everywhere. Okay, you can graph it and see there's no holes in it, if that's the way you like to work. Okay, so yes. Again, it's differentiable. Once those two things are confirmed, then you could go to your f prime of c equals f of b minus f of a over b minus a. So f prime of c, so I plug c into this expression, and I get -3e to the -3c, right? On the other side, then, what do I have? F of 2, so I'm plugging 2 into this expression. I get e to the -6 minus f of 0, so e to the 0 is just 1, all over 2 minus 0, which is 2. Right? This is an exponential equation. I'm trying to solve for c. All right, so I need to get this term here isolated, this factor isolated. So divide both sides by -3, or multiply by -1/3 if you wish. So e to the -3c is, and if I move the negative to the top, it'll be 1 minus e to the -6 all over 6. Take ln's on both sides. Okay. So I get -3c equals ln of this mess. And then divide both sides by -3. Oh, sorry. What the heck am I doing? I didn't already do that? Oh no, it seems like I already I divided by -3 here. I gotta do it again. I thought I was in, oh, okay. So -3 down here, and that's pretty much the answer. I mean, you get a decimal approx for it, but I just go with that. There it is. There's your answer, buddy. All right. Right. So the next part is something that I hope you caught in the video, and this is how I want you to do the presentation for relative extrema. So number 7, we have a lot to do actually. Find the potential critical numbers of the function, draw the number line, do the test values, determine signs, make conclusions, and finally use the first derivative test to find the relative extrema, right? So there's a lot going on in this problem. And I want you to do a sign chart. The book does like a table, but I want you to do the sign chart for me, okay? And I need to see all of this information when you do it. Okay, so let's go at it. This is number 7. So I have y equals -2x squared plus 4x plus 3. Okay. I need the derivative. So y prime is -4x plus 4. Then I need the critical numbers, so where y prime is 0. -4x plus 4 is 0, so 4x equals 4, so x is 1. And then where is y prime on it undefined? And that never happens. It's a polynomial, it's a line. There's no holes in it. Okay. And then what do? Well, I'm going to draw a number line, which represents the sign of the derivative. Okay, so this is the derivative. And I always like to put a little marker here, f prime of x, to remind myself this, I'm working with the derivative number line. Okay? When I do my tests, I have to plug into the derivative. Okay, I'm only going to label the critical numbers. Okay? So I just put 1. Don't put 0 on there. It's going to confuse anybody who has to grade your work. Okay. Okay. Then I need test values. I need signs, conclusions, and then I need to find maxes and mins depending on the signs. Okay. So test values, pick any value in the interval from -infinity to 1. I'll pick 0. Plug that into the derivative. So that will be 0 plus 4 is 4. I just need the sign of it. I don't need the answer. It's just whether it's positive or negative. Okay? And then finally, make your conclusion. If it's positive, that means the slope is going up. So you can think of that way, and the function will be increasing. Okay, okay, over here, let's try x is 5. So negative 20 plus 4 is a negative number, so negative. That's decreasing. Okay? And then if the graph is increasing and then it decreases, it'll have a hill and there'll be a maximum on top of the hill. So you could say there's a relative max, I'll just write max, at 1 comma f of 1, and now you need to go back to the original function. Okay, so negative 2 plus 4 plus 3, 7, 5. Okay. There's a relative max at 1, 5. So you really need all of that for these problems to pan out for me. Okay, so I can understand what you're doing and give you a good grade. Okay. Okay. Let's try number 8. So there's like 3 of these on the test, last year's test. This year's, you know, it might have to be a take-home, so the problems will be a little harder. Okay. Okay, but the general ideas are always the same. Whoops, I should have gave you the function first. Let me give you the function first. So there's number 8. Y equals x plus 2 to the 2/3. Okay. Okay, I need the derivative, y prime. That'll be 2/3 times x plus 2 to the 2/3 minus 3/3 is minus 1/3. Okay. And my lighting isn't the best. All right, so I need to find where the derivative is 0. Okay, so I set this equal to 0, have 2 all over 3 times x plus 2 to the 1/3 equals 0. And then if you multiply both sides by the denominator, you get 2 is 0. Well, we know that then has no solutions. So no help there. And then I want to look for where this thing does not exist. And clearly, if you look at this expression, which represents the derivative, that's when the denominator is going to be 0. So we're just going to take that denominator. Right? And then this is clearly 0 when this is 0. So in other words, when x is -2. So that'll be our only critical number, and we'll go to our number line now. Okay. Okay, so here's my number line. I'm going to mark it f prime of x, and then I'm going to consider -2, and I need test values, signs, and conclusions. Okay. So I'll try x is -5, and I'm working with the derivative here. Okay, so you're plugging this into here. If you have 2/3 times -5 plus 2 is -3. The cube root of -3 is still going to be a negative. Okay? So it'll be a positive times a negative. In other words, it's negative and it's decreasing. If you don't get negative, try putting it into to this object. Right? It'll be a positive over something that ends up being negative. Okay? The cube root isn't gonna. It's not like a square root, you know. It's or a square. It's not going to make the negative go away. If you had a square root, you'd be in trouble. Anyways, let's try x is 0. If I plug 0 into here, it'll be 2 over 3 times 2 to the 1/3. That's a positive over a positive, which of course is positive. It means it goes up. Right? So you're going to have relative min at -2. So relative min at -2 comma, I guess it's, if you put in -2 into here, you'll get 0. Okay. All right. Seems like I made a mistake somewhere on my, oh yeah. All right. Okay, so anyways, there it is. All right. One more of those. And this is number 9. So we have an ugly one. Y equals x squared all over x squared minus 9. Okay, so to pull this off, I need to do low d high minus high d low. So y prime is going to be low x squared minus 9 times the derivative of the high minus high times the derivative of the low all over the low squared. Okay, clean it up. So we get 2x cubed minus 18x minus 2x cubed. And that'll be all over x squared minus 9 squared. And the 2x cubes will cancel out and get negative 18x all over x squared minus 9 squared. Okay, so again, we want to know where does y prime equal 0 and where is y prime undefined. For y prime equals 0, you just take the numerator and set it equal to 0. And you would get one critical number of 0. And then we also know where is this thing undefined. So you take the denominator and set that equal to 0. And that'll equal 0 when x is plus or minus 3. You just kind of look at it and know, right? All right. So 3 critical numbers, or potential critical numbers. These guys aren't technically critical numbers, but we pretend they are potentially. So we use them when we do our graphical analysis. Okay? Okay. So here's my number line for the derivative, f prime of x. I'm going to label just the critical numbers. Okay? So -3, 0, and 3. Okay? And then I want to do all the test value, etc. Right? So test value, sign, and my conclusions. And I'm working with the derivative. Okay? So if I try x is -5, the denominator is automatically positive. So the only thing that's going to affect the sign is the numerator. A -18 times -5, negative times negative is positive. It'll be a positive over positive, which is positive. So it's increasing. You try x is -1. So for the same reasons, it's going to be increasing. If you try x is 1, it'll be a negative times a positive, so that'll be negative, decreasing. And then in here, let's try x is 5. Positive times a negative is negative, and that's decreasing, right? Okay, so what? Well, it looks like we have a relative max at 0. These, whenever you have the direction going the same around a critical number or a potential critical number, there's no max or min there. I mean, truthfully, if you look back at the original function, it's not even defined at 3 or -3. So there's nothing there to be a max or min. Okay? Look, so there seems to be maximum because it's going up and then down, so there's a hill there. There's a relative max at 0, comma, and you plug 0 into the original function here. You'll have 0 over -9, which is 0. Okay. Whoop. There's that. Those are first derivative problems. The second derivative tells you more about the kind of curviness of the curve, right? It's the concave up, concave down idea. So if you have, for example, a parabola that looks like this, it is concave up. If you have a parabola that looks like this, it's concave down. And then we have little guys that are kind of like this and go like this. So whenever you kind of see this S-shaped object, that's going to be an indicator of an inflection point. Okay, so it's concave up, in that interval, and then it's going concave down in the next interval. Okay? So when that occurs, then you have an inflection point, and you'll see it in your analysis. It will concave up, concave down, unless it's undefined. Okay, so that's the issue at hand for the next set of problems, like problem 10. We're looking for concavity, and I start you out with a nice easy polynomial. Right? Okay, so y prime is going to be 4 times a half is 2, x to the 4 minus 1 is 3, plus 3 times 2 is 6, and then x to the 3 minus 1 is 2. Right, so I need to find where that's 0. So I have 2x cubed plus 6x squared is 0. I'm going to factor this, so 2x squared, and I'll have x plus 3 is 0. Looks like I'm getting two critical numbers, or potential, well, oh, I don't need to even do this for this problem. I should have read my directions, right? For this problem, all I need to do is find the second derivative, find the potential points of inflection, draw a number line, do tests. Okay, so I don't need the first derivative info. Sorry about that. So go to the second derivative. I have 6x squared plus 12x. Then that thing, you set, it's the same thing as finding critical numbers. You set this equal to 0. Okay, so I'll have 6x times x plus 2 is 0. So x is 0 or x is negative 2. And then the second derivative exists everywhere. So for the second derivative not being in existence, there's nowhere that will happen. So I just put none there. Okay, now I go to my graphical analysis. So this time I have the second derivative to work with. So f double prime. I'm going to plot the two potential inflection points. Okay. And then I got to do all my busy work. I have to do my test value, my sign, and my conclusion. This time you don't need maxes or mins. Okay, that's not going to be required of us. So x is negative 3, and I'm going to go to the second derivative. And it's probably easier to work with this form, as long as it's algebraically equivalent. Then you can work with the simplified version. Okay? So I'm just going to plug stuff into here. So if I plug negative 3 in there, I'll get a negative 18 times negative 1. Negative 3 plus 2 is negative 1. That will be negative times negative, which is positive, so it's concave up. And I'll try x is negative 1. Plug negative 1 in there, negative 6 times positive 1. Negative times a positive is negative. That's a sad face, concave down. And try x is 1. Okay. So I plug 1 in here, I'll get 6 times 3, positive times positive. That's positive, concave up. And that's all you have to do for that problem. Okay. Well, okay, let's look at two more. Fun stuff. Okay. Number 11. We have y equals 24 all over x plus 12. Okay. I'm going to rewrite it. Right? So it's easier to take the derivative. Okay, so y prime will equal, bring down the negative 1, I get negative 24 times x plus 12 to the negative 2 times the derivative of x plus 1, but that's just 1. Okay, then I need to get the second derivative, y double prime, bring down the negative 2, so that would be 48 times x plus 12 to the negative 3. Okay. And if you want to, you could rewrite it 48 all over x plus 12 cubed. Okay, I need to find where is the second derivative equal to 0. I'm looking for potential inflection points. Right? And clearly, if you set the numerator equal to 0 and go that way, okay, there's no help there, right? That thing will never work. There's no solutions to that resulting equation. Then I'm going to look at the second derivative and find where it does not exist. Now this time, if you take the denominator and set it equal to 0, you'll find 12, negative 12 rather. Right? So when x is negative 12, this thing will equal 0. So I'm getting one critical number, or sorry, potential inflection point this time. Right? So I go to my graphical analysis for f double prime of x. Here's my potential inflection point. And I'm going to do test values, signs, and conclusion. Okay. So for test value, I'll try x is negative 12. Whoops, can't use that one, right? I can't use the actual value of the critical one. So let's try negative 22. So if I plug that into here, I'll have a negative cubed. A negative cubed is still negative. Right? I'm working with this, the second derivative. So I'll have a positive over a negative, which is negative, which means concave down. Let's try x is 0. In that case, it'll be positive over a positive. So it'll be positive, and that'll be concave up. Okay, and that's all you need. One more, it's a trig. Okay. So 12. Y is sine of x over 2. And then we're going from the interval 0 to 4 pi. It's still working with second derivatives and getting the graphical analysis. Okay, so y prime is cosine of x over 2 times the derivative of x over 2. The derivative of x over 2 is 1/2. And for the second derivative, I'll have 1/2 times the derivative of cosine is negative sine of x over 2. And again, by the chain rule, you have to multiply by the derivative of x over 2, which is 1/2. So at the end, I have y double prime is negative 1/4 sine of x over 2. Okay, so I'm setting it equal to 0. And so I'm looking for where is this thing equal to 0. And that's going to happen when sine of x over 2 is equal to 0. And that'll happen when, if you think about your unit circle now, will happen when x over 2 is equal to 0, pi, 2 pi, 3 pi, 4 pi, those things. Okay. So we want in particular the x values, right? So if you multiply both sides by 2, then you'll have x equals 0, 2 pi, 4 pi, 6 pi, etc. And of course, there's negative ones on the other side, but we won't be using those anyways. Okay, so which ones are in our interval? So we're trying to find the ones from 0 to 4 pi, right? And that'll be these characters right here. The 2 are on our endpoints, so this is kind of maximizing on a closed interval, right? At the endpoints, I'm not really going to care too much about what's going on for concavity, right? With maximizing and minimizing on closed intervals, I would have to consider the endpoints. But here I don't have to. So on the number line, I'm just going to draw some brackets here at 0 and 4 pi. This represents the second derivative. Right? And then I'm going to label 2 pi in here. I just need to find the concavity on either side. So you're going to need test value, signs, and conclusions. Okay. So test value, I'll take pi and 3 pi. So when x is pi, I go to the second derivative. I'll have pi over 2, sine of pi over 2 is 1. 1 times negative 1/4 is negative, so I have concave down. plug 3 pi into here. Sine of 3 pi over 2 is -1. Negative times negative is positive, so it's concave up. Okay. Okay. Limits. Limit problems are actually real easy once you get the hang of it and you wrap your brain around what's going on. Okay. So we have this object. And when you're going towards infinity like this, you're looking at end behavior. In this case, it's going to negative infinity. So in that case, you can kind of just look at these terms because everything else is going to be so small, it won't really matter, relatively. Okay, okay, so I can rewrite this as just having this, it's just going to have the same behavior as x all over the square root of x squared. Okay. Look, now I have to be a little careful with this critter, right? The square root of x squared is actually the absolute value of x. Okay. The absolute value of x is two different things. It's negative x if x is negative, and then it's positive x if x is non-negative. Okay. So in this case, the input values are all going to be negative. So this thing will be negative x. So it's going to be the limit as x goes to negative infinity of x over negative x. Okay. And then you could simplify that. That's just -1. And the limit of a constant is always just the constant. I'm running out of room there, so that's equal to -1. Sorry for squishing that. Okay, so you have to be careful when you get these guys. Okay? Otherwise, it's kind of just smooth sailing. You just kind of circle the high degree terms and simplify. Okay? So let's look at 14. We have the limit as x goes to negative infinity of x cubed minus, I think it's minus, no, it's plus 5 all over 5x squared minus 2. Okay. So again, I want to just isolate the high degree terms. That'll be all of that junk. Okay. And the resulting limit will just behave as if it were the limit as x goes to negative infinity of x cubed over 5x squared. Right? And then I can simplify this thing. It's the limit as x goes to negative infinity of x all over 5. And then it's just asking where does the line x over 5 go as x goes to negative infinity. Okay, so we can draw x over 5, up 1 over 5. It's going to look like this. Okay? And as x goes to negative infinity, x over 5 is going to where? Well, it's going really, really far down. It's for whatever negative value you give me, I can find a negative value that's less than that. So it's going to negative infinity. Okay? So if you look in this direction, as x goes to negative infinity, the y values are going negative 100, negative 1,000, negative a billion, negative a gazillion. So it's negative infinity. Okay, 15, limit as x goes to infinity of x squared plus 1 to the 2/3 all over, I think that's an x. Yeah, x plus 3. Okay, so again, I just look at the high degree terms, and I need to kind of borrow the exponent for that, because that exponent does apply to this. And this will behave the same way as x squared to the 2/3 all over x. And then just simplify that. So using my exponent rules, x to the 4/3 over x. Okay. And then we have the limit as x goes to infinity of x to the 1/3. And then that thing, where does it go as x goes to infinity? Well, x to the 1/3 looks like this. Right? So as x goes to infinity, this thing is going really slowly up and up and up and up. So it's going to go to positive infinity. Number 16 is kind of a foreshadowing our work with sequences in Calc 2. We'll do all kinds of sequences there. So we have the limit as n, as a nanofiber, goes to infinity of 2n plus 1 over n plus 3. And don't lose your cool. Just go ahead and isolate the high degree terms again. Instead of x's, we just have n's. And we have 2n over n, which is just 2, and the limit of a constant is a constant. That's equal to 2. All right. Let's look at number 17. So we have some special limits, in particular, the limit as x goes to infinity of e to the negative x. Right? That e to the negative x, you can drop it down to the denominator and write 1 over e to the positive x. Then you're plugging in things like 10, 100, 1,000, a million. So it's 1 over e to the 10, 1 over e to the 100, 1 over e to the million. So it's going to be like 0.01, 0.0001. It's just getting really close to 0. The other special limit, x going to negative infinity of e to the x. And this works the same way as this. Okay? They're equivalent. So this will also be 0. In this case, instead of plugging in like x equals 10, x equals 100, x equals 1,000, you're plugging in x equals negative 10, x equals negative 100. So when you put it in here, it'll be like 1 over e to the 10, 1 over e to the 100. It'll be the same thing as this. Okay, okay, so there's two special limits. And we could use that to do number 17 and 19. So number 17, we have the limit as x goes to negative infinity of 3 minus 5 e to the x. So that was one of our special ones. This part will just go to 0, and we have 3. Number 19 is of critical importance these days because it's the logistic growth equation, right, which is often used in modeling pandemics. Right? So on the news, you'll hear people say, oh, we have exponential growth, right? But the truth is, and not like the ultimate truth, but the truth really is that there's a limiting capacity to the number of people that can be infected. Like if there's 4 people in my household, there's not going to be 5 people being infected, right? So an exponential curve looks like this. The exponential growth will kind of look like an exponential, but then level off. So the leveling off would happen once we reach to the population of the United States, right? And during pandemics, I mean, that's kind of what's going to be occurring. It's not necessarily an exponential growth. Maybe in the beginning, yeah. So I don't know. I'm not a modeler, but you look it up. Logistic growth equations, if you're interested in that kind of stuff and pandemics and working for the CDC someday, I don't know. You might want to Google that logistic growth thing and find, okay, so anyways, this is that. And here the limit of the whole is the limit of the parts, right? So the limit of 10 is 10. The limit of 1 is 1. The limit of 2e to the x is one of our special limits. And it should be, sorry, negative x, right? So that thing will go to 0, and we'll just have 10 over 1 minus 0, which is 10. Okay? And the limiting capacity of these kinds of equations is always going to be in the numerator. Okay, anyways, number 18. Find the limit as x goes to infinity of arctan of x over 3. So arctan looks a lot like the cubic equation, but it's not because it has asymptotes, right? Tan has asymptotes at negative pi over 2, and, well, you know, x equals negative pi over 2 and x equals pi. Arctan has asymptotes at y equals pi over 2 and y equals negative pi over 2. Right? So as you go out further and further in the x direction, as x goes to infinity, the y values will get closer and closer to pi over 2. The fact that it's x over 3 won't really affect it. It's just going to mean it's going to get there a lot quicker, or a lot slower, rather. So when this, if it was just arctan of x, okay, this thing, when it's at 30, would be, this thing when it's at 10 would be where this thing would be when it was at 30, right? So it's just a matter of where your x values are, but you can kind of make this correspondence between them, okay? They're the same thing overall. So again, what I'm saying is that if you look at a sequence going to infinity where it's 30, 300, 3000, all you need is the end behavior. So if you look at, so I'm putting in numbers like that into here, and when I put them into here, I get, well, what 10, 100, 1,000, right? So if you're doing an analysis on this, you'd likely use these numbers, but you'll get the same numbers in the output as though you had put it in 30, 300, 3,000 into this guy, right? And so this guy is just going to get to pi over 2 slower than this guy, is what I'm saying. Okay? And if you think about it for a second, when you divide by a number, it's going to stretch it out horizontally, right? So that was all of our computations with translations of graphs. Okay, I'll shut up. Next problem, 20, is a maximization problem. So in maximization problems, you'll have you want to find two equations, constraint equation and the equation you need to maximize or minimize. Okay? So in particular here, find the length and width of a rectangle that has perimeter of 110 meters and a maximum area. Okay? So draw a picture. It's a rectangle. I'll go X and Y. They tell us the perimeter is 110, so that's our constraint equation. The perimeter is 110 meters, so 2x plus 2y, that's from basic geometry, equals 110. That's the perimeter, the walking distance around the rectangle. And then the equation we want to maximize is the area. And right now, the area is in terms of x and y. X times y is the area. So it's a common theme in these problems. You use the constraint to reduce the number of variables in the maximum or minimum function. Then you take the derivative, find the critical value, and that's usually your solution. Right? Okay, so I use the constraint to reduce the number of variables. Right, so I'll solve for y. Then I use this to reduce the variables in the thing I want to maximize, right? So this means that a is now equal to x times 55 minus x. Okay, then I take the derivative of this thing. So a prime, and I probably want to distribute this and think of the derivative there. So 55x, when I distribute it, its derivative is 55. Minus x times x is x squared, so its derivative is 2x. Set it equal to 0. And I get x is 55 halves. Right? Then I find my y value by plugging it in there. So y will be 55 minus 55 halves, which also is 55 halves. Okay. So at the end of the day, the dimensions are 55 halves by 55 halves meters. Okay. Okay, so that's how I want things presented. You know, if you learn nothing else from this chapter, I hope that you would at least be able to present this in a nice, perfect fashion, and so on. Okay, so like I said, I don't know how we're going to do tests really yet. I may have to do a bunch of like projects or something, but this is like bare minimum stuff. Okay, you need to have this, or there's no way you can go forward in the Calc 2. Just no way. Okay? This is bare minimum stuff. All right. not to scare anybody. So there's always a way, there's always tomorrow. Okay, you can always go back. It's never too late to be educated. All right, don't forget that. I'm just saying that, you know, if you're in a hurry to get through your degree and you're cutting corners, ugh, it's bad news. It's better to iron it out now first before you get in too deep. Okay, all right. I don't